All right. Hello, everyone, and happy Wednesday. My name is Maddie Horsby. I'm the project manager for the Riot organization, and welcome to the Riot Lunch and Learn series, the place where we spotlight Riot sponsors. Today, we have with us TIBCO to speak about identifying anomalies in real time with edge analytics. Just a couple quick reminders before we get started. This event is being recorded and will be posted to Riot's YouTube channel and uploaded to the meetup page where you registered for this event. If you have any questions throughout the presentation, feel free to place those in the chat and I will be monitoring those throughout the presentation and we'll answer those at the end. And please keep yourself muted. With all that being said, I will pass it over to Ahmad. Ahmad, thanks so much for joining us.
Absolutely. Great to be here. And hello, everyone. Thank you for joining. Today, we're going to have a really interesting and fun technical problem. I'm being joined by technical problem to discuss, not the technical problem in the presentation. It's a really good one. I'm being joined by two of my colleagues, Marcelo Gallardo, who's a senior solution architect at TIBCO, and Atir Alatar, who's a lead data scientist at TIBCO, and I'm a director of data science, Ahmad Fatahi, here. So this is the usual confidentiality and disclaimer slide. So what we're going to go over today is a quick introduction of TIBCO as a company, who it is, what we do here, what's our purpose in life, and then we quickly pivot into the problem that we're going to talk about today, which is an end-to-end from the edge all the way to building a model on servers, or it can be in a cloud environment, and deploying it close to the edge and seeing the results, and we basically close it from there. In terms of what we are as a company and what our purpose in life is, a lot of what we do eventually ends up being at the service of bringing intelligence together. So we are a software company. And everything we do is about connecting intelligence. Starting from the left-hand side in this triple infinity loop, the connect side, where there are disparate sources of data across the organization or any organization. It has to be collected and then unified together, which means the different shapes and different technologies, databases, streaming with data at rest, all of that needs to happen. And then analytics on the top, which internally we call predict. It's basically adding analytics. It can be simpler or more rudimentary, all the way down to deep neural networks and more advanced types. To dig a little bit deeper into these three pillars that we cover at TIBCO, it's really hard. So it says impossible to emphasize the fact that, especially for large organizations, for older organizations, it's often quite challenging to get this done for organizations that are used to doing things for decades, in many cases, many decades. Doing things in a certain way, even connecting to pieces of equipment, many of which can be even still analog. They don't even support a digital sensor, to begin with. Challenges of that sort, all the way to cultural challenges and overcoming barriers where employees are very much used to doing things intuitively without high reliance on data. So all of that is what we are trying to tackle and enable our customers to do. To pick a few examples when it comes to our products and capabilities in each pillar. So when it comes to connect, we have a lot of products to manage and a rich set of capabilities to manage APIs, to connect and integrate in a secure way. Also work on or support events where there's streaming. Under Unify, I touched on organizing different sets of data. Also, another piece I would very highly emphasize is master data management, which is a huge topic. As soon as any serious organization becomes really data oriented, the employees need to not only be able to discover what data is available, that becomes a challenge. Also, it has to be granular enough, so the right people have access to the right data and nobody else. And when it comes to the analytics part under predict, like pretty much everywhere else, it usually starts from the exploratory data analysis. Visual analytics goes a long way, and our marquee product Spotfire is a poster child of enabling that with really dazzling visual analytics features that are not just out of the box, but also extensible. So fairly easily anybody can customize and build their own visualizations, down to supporting data science new models and inference on streaming data. From a different angle, if we look at how the business works, we're present in several different verticals pretty actively. I would just looking at some of the stats on the right hand side, you can see biotech, transportation, energy and utility manufacturing. These are some of the ones that finance, actually banks and insurance companies. Those are some of the verticals that are really our bread and butter, and we're in ways that the standard analytical and data tool for these verticals. And so what we're going to talk about and touch on today to connect it to our problem at hand, we are going to talk about the problem that can very easily connect to use cases in manufacturing, transportation, healthcare, wherever there's a sound signal that people need to, maybe even energy, and people want to make inferences based on the sound in the environment. Looking at this structure or the architecture of our products, the thought process is, if you look at the left-hand side, that's where the data happens. It can be the sensor, it can be a database, and like I said, it can be data address or data in motion. One stage to the right, one step to the right, it has to be stored and also serve to the rest of the organization, be it the users, the humans, or other applications in a manageable and secure way. And all the way to the right is where the analytics happens, where as you can see, there are visual analytics in that box, as well as where people write code and everything in between, and all of that is supported. If in slightly more advanced cases, there's some level of analytics happening in between, so it's not just raw data being shipped to the analytical layer. That's where your the middle box under analyze, your data science happens, either in the training mode, or the bottom box is in the runtime engine or runtime mode. And then all of that has to be operationalized. So managing all the models in the deployment phase, or model monitoring, all of that is something that the model ops box takes care of. And to orchestrate all of the above, these two boxes on the bottom left and right, on the data side, I refer to master data management, which is important, both cataloging the data and making it secure. And on the right-hand side, at the consumption layer, managing the APIs. That's something that is critical to any serious organization. This is the neutral architecture or set of boxes of capabilities that any data organization need to serve. Now, to overlay this with TIBCO products, I just changed the labels here to say which products, which TIBCO products support these functions as a reference. I'm not going to go through every single one of them. It would take a totally separate session. But as you can see, we support pretty much all of these boxes. What we're going to talk today about, or cover today in our user story, is depicted in these green arrows. So we're gonna follow a story where starting from the bottom route, actually, we're going to talk about data being collected and a model being trained. And then once it's deployed in the field or at the edge, we apply that inference to streaming data or data in motion. In any organization with our products, we're touching the lives of several different personas, from data scientists to business analysts, and if you zoom out one level, the architects and the DevOps engineers and MLOps professionals. And I'm not going to talk too much about this theoretically, because we're going to see a lot of that in action when we actually talk about the problem. Different personas are going to be present. All right. So now that we have established who we are, what TIBCO does, this is it's getting closer to the fun part. So I'm going to talk about the problem at hand for today, and what our approach is. So let me go back one slide. So the analogy is actually very close. It's not even an analogy, it's almost identical. So many of us know people who are very good at listening to a car engine, while it's running, and just, by intuition, after a few seconds, they can tell you that, yeah, this car sounds okay, or no, something's off. If they're even better, they can even tell you not only it's off, but also, hey, I think like, that, the belt and that belt in the engine, it sounds like, and that's the key phrase, sounds like the belt is wearing out. So that is awesome, but the problem with that is it's not scalable. You cannot, if you imagine a large manufacturing environment with lots and lots of pieces of equipment, engines, pumps, fans, which is actually the case for our presentation today. The data is from fans. You cannot have human beings trained and intuitive human beings listen to them at all times. So what we're showing today is automating that process and building that intelligence with data and software and our software, so that there's an engine always listening to your pieces of equipment, identifying the normal modes and the abnormal modes. And to motivate the problem more formally, this is the setup for any maintenance process or decision making in any manufacturing or energy environment. So on the left hand side, on the bottom left hand side, the curve is basically the probabilistic curve of any piece of equipment that has been developed by just gathering data from the field. So empirically, this is what we have. We can develop a distribution of how long it takes, or what's the likelihood of this specific piece of equipment to go down after n number of days or n units of time past its last maintenance. With that in hand, what we are seeing on the top right, you can associate cost to two events. So anytime that there's a piece of equipment that's running, we take it off, it's planned, and we maintain it to put it back on, there's some cost for that scenario. Another cost is associated with an event where it's unplanned. So we just let the equipment run, and at some point in time, it just fails. It can be by design. Some organizations may feel like that's the best they can do. Just wait until it fails and then they fix it. Or in some other cases, it's actually not expected. It's not planned, or it's not by design. It just unexpectedly fails. So which has its own cost. So the curve on the bottom right is actually depicting that, turning that cost per event, and the curve on the bottom left, the probabilistic curve, into expected cost. So there are two curves, as we are seeing, the green one and the salmon one. The x-axis is how much we wait after the last maintenance in units of time, and the two curves in green and salmon are the expected cost. And at any point in time, we are facing both costs. So the total cost is what we are trying to optimize as our expected cost. That's what we are trying to do theoretically, to model that and then eventually minimize. From the more anecdotal evidence, there's significant amount of research from the field, from the analysts, on the cost of unplanned failures of pieces of equipment and the value of predictive maintenance to across industries. Obviously, it will be very dependent on which industry and which use case. This is a very high level view of it. And everywhere we looked, there's a very significant upside to applying predictive maintenance, to adding it to our industrial environments. And this is just one aspect of, like, 20% increase in productivity, and 50% as a partially as a result, 50% increase in IoT use cases. Specific to predictive maintenance, these are very, very significant numbers on the right-hand side, as you can see. I leave it here, this slide, for a second as a reference. Just motivate. These are not tiny numbers. These are huge numbers. And if you're familiar with any sort of industry, I cannot even think of a single industry where this problem would not be a significant improvement to their operations. So it's a very, very much transferable and widely applicable problem. Who would be interested in this? Starting from the right-hand side, the maintenance technician. She would every day, every hour at work, she has to make a decision. Do I tend to this piece of equipment or that one or that one? And what we're seeing today is going to help her be way more targeted in actually going after those pieces of equipment that are in need of maintenance, as opposed to random or just relying on intuition. The second column in the middle is the manager, one level higher in terms of the leadership of the company. They will be able to not only run a more efficient team, but also it's better, team job satisfaction, because they feel like, they're actually doing things that are targeted and more impactful, as opposed to just random or scheduled mechanical tasks every day. And all the way to the left is the executive, who can save a lot of money by basically based on all those numbers, analyst numbers that I showed on the earlier slide. And so let's start to dig deeper into the problem. On the left-hand side, the data is being gathered from a piece of equipment. In this case, this is the sound data collected through a microphone sensor, which can be run on a very small footprint, like a Raspberry Pi. Pretty much everything we are seeing here later in this presentation are containerized solutions and on a very small footprint. So when the sound signal is collected, it's passed over to this intelligent engine in the middle that's being trained and deployed in the field, which then results in predictive maintenance based on that model that applies intelligence. The architecture is like this. The bottom tier is the data, where data is being gathered by the sensor, the microphone in this case. It's passed up one level to the intelligence tier, where in the middle box of the middle tier, that's where the model building happens. To the right of it, TIBCO Spotfire is the visual analytics layer. which goes a long way in enabling any data scientist to be able to look at the data, and before they build the model, then they build the model in the middle one, the TIBCO data science product. And on the left hand side is the hard project Air, as we'll see in a little bit by Marcelo. That's the specific engine that's built for streaming data enablement from these tiny devices in the field, both for passing the data, building those data pipes, as well as applying intelligence in real time once the model is built. And last but not least, the top layer is the consumption layer, where once the intelligence, the inference is produced, it can be consumed in any shape or form you like or fits your business. It can be a dashboard. It can be very well done in our own Spotfire, but that by no means is the end of it. It can be done in any environment, like a mobile app, or a notification email sent. It can be tweeted out, whatever you like. It's extensible. All right, so with that, Marcelo, are you ready to walk us through Project Air?
Thank you, Ahmad. Yes, so could you please keep your screen, and I will just talk to your slides.
Sure.
Hello, everybody. My name is Marcelo Gallardo. I am a member of the TIBCO Labs team. And in this part of the session, I will give a quick overview of Project Air and show some of the capabilities. So what's Project Air? It is an open source initiative from the TIBCO Labs program, and it aims to bring intelligent insight from the devices to the boardroom. This is accomplished by allowing users to easily register and interact with any kind of IoT device, process the device data at the edge or at the cloud or wherever it is needed, and also be able to run any edge devices or cloud provider. We also provide capabilities to store and analyze the data as needed, and allow to extend every layer of the architecture for easy integration with other platforms. Next slide, please. So in summary, Project Air provides capabilities for connecting to devices and processing the data they produce, managing the data from the devices, creating triggers and flows to respond to IoT events, store data into long-term big data repositories for historical analysis and analytics, being able to visualize the data produced by these devices, and also providing a customizable UI to monitor, measure, and react to these events. So how do we accomplish this? Next slide, please. So Project Air is laid on top of EdgeX framework, that is an open source project from the Linux Foundation. So we can see on this architecture on the left-hand side, we have the devices itself, and then on the middle where it says Project Air, the red box and the purple box, that's where Project Air runs. And this component can run either at the edge, or it can actually run at the cloud if desired. And on the right hand side is pretty much the backend applications that usually run on the cloud. So on the left hand side, on the purple box, the Project Air relies on EdgeX framework. This framework provides a layer architecture on the left-hand side of the architecture with the ones that interact with the devices. We can see there's a series of services that are interacting directly with the devices. This EdgeX device service translate information coming from the devices via hundreds of protocols and formats, and bring them into EdgeX. In other terms, the device service ingests the sensor data provided by the devices. And when it ingests the sensor data, the device service converts into data produced and communicated by the thing into a common Ajax data structure and sends that the converted data into a core service layer and other microservices and other layers of the Ajax Foundry framework. And that's where our framework is laying on the right hand side. We are consuming that data that has been converted into a common format here. That's what I will show you now. I will provide a demonstration of the Project Air user interface and how we actually consume that data coming from the devices. So Ahmad, if you can give me control, please, I will try to give a quick demonstration of. But still, you need to give me permission to share my screen. Okay. Just 1 minute.
Yep, Marcelo, you should be able to share your screen now.
Okay, let me try it now. Can you guys see my screen now?
Yes.
Yes.
Okay, so when you log into Project Air, when you start working with Project Air, you get into a welcome screen and you can get started. The first thing that we present is a dashboard, which gives you a summary of all the different devices and things that you are managing. And we organize these devices by groups. And here I have a group called Hello World Group, and we usually call these gateways. They can represent different locations or different group of devices in the same location. Like, for example, if you have a factory with thousands of sensors, you might want to split those devices into different groups. So once that you have your devices here, you can actually see and manage those devices. Here, for example, if I click on the view details, I can see that here in my house, I am monitoring 2 devices. One is the fan that we are going to use for this demonstration, and one is another simulator device that is that's receiving REST events. So I can send the events using the REST interface. And on the top, here we can see the different sensors that we are simulating with this device. So here we can see a sensor that simulates readings from a float, of type float. And here, when you click on that, we can see that we provide the details of that specific sensor. For example, here we can see that this sensor is sending data of type float. We can see the minimum value, maximum value, and at the bottom, actually, we can see a history of the data that we have received. In this case, we haven't configured anything, so we cannot see any data that we have received yet. And same thing for other data types. You can just go for, like, for example, string reading. And here we can see actually a couple of sample data that I have sent to with the REST interface to this sensor. Another functionality that we provide with the user interface is a way to actually create business logic with the data that's received from the devices. So the first thing that you need to do is we allow you to configure how to receive that data and work on that data. So here we have an icon called endpoints, and when you click here, we take you to a screen where you can configure different things that you can use in your data flows. So in this case, we have configured here some MQTT brokers, one that is specific for Ajax, so we will be receiving the data from Ajax here using this channel. And you can configure other protocols. In this case, I am using MQTT, but you can also use Kafka or AMQP as the protocols to receive data or send data to other locations. Like in this case, we have configured another MQTT broker. This is the Air application that's running on the backend that actually will receive data from the sensors and will store in a data store that we used here by this user interface to display the data that I am showing. Another thing that you can configure is different data stores where you can save your data. In this demonstration, I am going to show that we are receiving the data from this fan. We will receive some sound samples, and we will store in a Postgres database. And here's again the connection to this database. And again, for this demo, we're using Postgres, but we also support some other data stores like Snowflake, Oracle, MySQL, and a couple of graph data stores. You can also configure REST endpoints. In this case, we have configured and deploy a model that is actually going to receive the data that we receive from this fan, and will send that data to the model, which will do the inference and tell us if there is a problem with the fan or not. So that's the way we define the endpoint to communicate with the model. So going back to the main dashboard, we can also then jump into actually defining this data flow. So here on the pipeline, we are presented with canvas where you can start creating your logic. So as Ahmad mentioned in the first part of this session, I am going to demonstrate like just collecting data from the fan and then storing into a database. That data in the database will be analyzed by the data scientists and apply machine learning, and actually the model will be created based on that data that we are going to collect from here. So I am going to start creating the data flow. So I select a data subscriber activity. In the data subscriber activity, you can select where you want to receive the data. So here I am going to select that I am going to receive from Ajax. You are presented with a summary of the endpoint that you're going to connect. And then the next activity, you can select from a series of activities that we have available here. So for example, in this case, we just want to save data from the fan, so we can create a filter activity here. And in the filter activity, we can connect, we receive the data, and then we want to filter. Let me icon this. So here we are going to select that we don't want to receive anything from the REST device. So I am going to filter all of these readings that are coming from the REST device. And I just want to receive the data from the fan. So I don't filter anything that is coming from the fan. And then the next activity is that we want to store this in the database. So we just simply say we want to put a data store activity. Let me see, where's the data store activity? Right here. And again, you connect the activities and then select the data store where you want to use. In this case, we have configured only one database. So we select the Postgres database. And here on the contents, we want to store the readings coming from the device only. In this case, we are not doing any inferencing, so we are not going to save any enriched reading. That's when we apply like inference to the data, and then if we want to save the results of that, then we will select this enriching reading. But for this case, we don't do that. So now we'll give it a name to this data flow. So we'll call it demo pipe. And here we specify where we want to deploy this data flow. In this case, we want to deploy it to the edge, close to the device. And as you can see, we can also have the option to deploy this logic to the cloud if desired. But in this case, we're deployed to the edge. And we specify what the deployer we want to use. In this case, we want to use the air deployer. And then we'll say the pipeline. And that's all you need to do. And then if we were ready to start receiving the data, we will just click deploy, and we will actually show you that when we actually configure the model. So for the time being, this is the pipeline we use to save the data and give it to the data scientist to create the model. So right now, Atir will be showing how he used the data that we saved with the pipeline I just demonstrated. Atir?
Yes, Marcelo, thank you. Let me share my screen. Okay. Can you all see my screen?
Yes.
Okay. So at this point, the data has been generated and ready from the edge as Marcelo did, and it's in a Postgres server. What we will do now, we will consume this data in order to generate a couple of machine learning models, evaluate them, and then we package these models and then give them back to Marcelo to implement them on the edge. The product that we're going to use here is TIBCO Data Science, and then TIBCO Data Science is an end-to-end machine learning and data transformation and cleansing platform that supports collaboration and supports also different personas from simple data exploration to advanced machine learning pipeline. It has a very collaborative environment where you can create workspaces, teams can work together, and then there is also a version control where you can track all the changes that you do on your model. It's a low code to no code environment. So most of the operations are existed in form of nodes here. You can simply drag a node and then connect it to your existing nodes. And with few simple configurations, you can create and run a workflow. It also leverages your local resources. So if you have a Hadoop server on premises, or if you have a Spark server on premises, you can simply tap into these resources from TIBCO Data Science. In terms of connectivity, you can connect to almost all the data sources and big data sources that are used nowadays. Let's see. Okay, so we can see here you can connect to for example, Cloudera, Postgres, AWS, almost all the data sources that are used in big data and machine learning. There's also another feature, it's called touch points, which is basically an interface to your machine learning model. If you are trying to share that model with business users or users that they don't want, let's say, interact with the details of that model, they can just go to a touch point, which is just like a window to your model where they can enter a few parameters and then run your model and get the results. So that's pretty much the TIBCO Data Science. In terms of what we are doing here, we tested 3 models. The first model is the autoencoder, and the second one is the isolation forest and local outlier factor. So in here, this is the data that is coming from the edge. We implemented three models, and then we tested the accuracy of the prediction for these models one by one. And then to do this, also we use the Python support in TIBCO Data Science, where you can simply create and script Python using Jupyter notebooks. So we implemented the script in these 3 models, and then we measured the accuracy for these 3 models and pickled the best accuracy model into like a PKL file. And then we handed this PKL file back to Marcelo to be containerized and implemented on the edge. So this marks the end of this step. Now we'll be back to Marcelo to talk about the containerization of the model and the implementation on the edge.
Thank you, Ati. Let me share my desktop again. Can you guys see my screen?
Yes.
Okay, so now that the data that we have, say, in the data store has gone through the process of machine learning and a model was generated from that, now we are ready to start inferring. We can receive the data from the audio that's generating on the fan and actually run through a model. So I have created an inference pipe similar to what I just did before, but in this case, we configured the data subscriber, and then I created an inferencing activity. The inferencing activity is actually the activity that's going to be calling the model and sending the data from the fan, as we can see here on the right. We have configured to send the microphone reading, that is the sample of audio that's coming from the fan, and we are sending to the inference engine. The inference engine will produce a prediction telling us what if the sound sounds good or bad, and then the result we will store again into a data store. And as I mentioned previously, in this case, I am configuring to also store the result from the inference in the data store. So now that we have finished with the configuration, project allows you to deploy these data flows very easily. So as we can see, the pipeline is safe. And now I will deploy. Before deploying, let me show you here. I have my Docker dashboard here. We can see all the different containers that are made up Project Air. And now I am going to deploy a new container that is equivalent to this data flow that I just have created. So you can see we have 4 groups of containers right now. So right now I am going to click, when I click deploy pipeline, what is happening is this configuration that I have created here is converted into application using a TIBCO Flow framework. That application is converted into an executable for the platform that we want to deploy this data flow. In this case, I want to deploy to my Mac. So it has to be compiled to run on the Mac. So that executable is created and then containerized and then deploy. So that's what I'm going to do here. I click deploy and we can see that the deployment was successful. So all these steps that I just described are going on behind the scenes. And we can see here, if I look in my Docker dashboard, we can see that this new container just pop up. And that is the one that I just created. And we can see the ID match the ID of this pipeline that I created here. So at this time, the data that we are receiving from the fan goes to the inferencing, and then the results are saved into a data store. So here I can bring up my Postgres data viewer, and I can see here a sample of some of the readings that we have received. So here, for example, if I click here, is a sample of the audio that we received. And also we can see a sample of the inferencing that the model generated the output. So in this case, it's telling us that the prediction is 1, and also it's giving us a factor, that successful factor that about the prediction. So as you guys can see, this is a very straightforward and easy to use. That concludes my demonstration. Ahmad, do you want to?
Yeah, absolutely. So to wrap it up, basically we showed. Let me put back up my slide deck here. Yeah, so in the past 45 minutes or so, we were able to show. Let me put back up this. This, by the way, this is a spectrogram of the wave file. So visually, the algorithms actually act on the visual representation of the sound signal. So if you're interested, we can dig deeper into this. But this slide is really, what I wanted to show. So let me go into this presentation mode. The everything we saw in the past 45 minutes was a depiction of these arrows that I showed earlier. To sum it up, we showed how a data engineer slash machine learning ops persona can use Project Air to connect to the data source and start collecting it, pass and store it in any data source. In this case, we use the Postgres. The business analyst slash data scientist persona then took it over, built the model, passed it to the machine learning ops persona, who then deployed the model at the edge. And then toward the end, the results will be depicted live to the subject matter expert. So we touched on all of these personas, and it will take a little bit of obviously learning. You know, some of the demos that we saw here rely on knowledge of the products. That's obviously granted, but if there's one takeaway out of this whole conversation is this whole end-to-end story was something that was enabled or easy enough for with our products, with TIBCO products and Project Air, that we could demo in 40 minutes. Actually, the first 15 minutes was my conversation, but that's the whole that's the big message, you know, to make that first message happen, you know, that you know, making the impossible or very challenging goal to happen at any organization. It takes all of this wide range of products and capabilities to make it happen. With that, I pass it back to Maddie. Hope you, everybody, hope you had you know, you learned something out of this presentation, thought-provoking, and we are here to answer any questions. I don't know if you have Q&A, Maddie. I don't know how the session works next, but regardless, we are more than happy to chat with you later in our contacts. I'll make sure that you have access to this recording and also our contacts if you'd like to chat with us later.
Awesome. Thanks so much, Ahmad. Wonderful presentation. Thank you, Marcelo. Thank you, Athir. Awesome. Well, I don't see any questions in the chat box, but at this point, I definitely encourage anyone who's still with us to feel free to throw some questions in the chat and I'll read those off to Ahmad, or feel free to unmute yourself and ask them a question directly. But in the meantime, Ahmad, did you want to go ahead and drop your contact information in the chat box just so that people have an easy way to access that?
Sure. Let me see. We might have a slide at the end. If not, I will. Yep.
Very cool. Great. Thanks so much, Jamie. Glad you found it was very insightful. Very cool. And just as a quick reminder, you know, Riot does have our YouTube channel where this whole entire presentation will be uploaded. So you guys will always be able to go back in there and access any of the information that Ahmad shared today. So that's a great resource. Cool. Well, Ahmad, I'm not seeing any questions, which means your presentation was extremely compensative and, you know, and everybody just really appreciated it. So I will let you guys go. I hope everybody has a great rest of their Wednesday. And as always, if anybody has any questions, feel free to reach out to any one of us, but thank you all.
Thank you.
Thank you very much, everybody.
Have a great rest of your day, everyone. Thank you.